Now that we have come up with this formal definition and notation for these double integrals, and we have an idea of what these regions or solids look like, now we have to turn to the matter of actually evaluating these things, right? And we're going to start by looking at these solids that are over a rectangular region, right? So what are those going to look like? Well, here is our XYZ space. And again, here is our surface. Right? And now what we're saying is we're going to be integrating over a rectangular region. So just draw a couple lines parallel to the y-axis roughly, and then a couple lines parallel to the x-axis roughly, and there's a rectangle. And again, we're going to start with this. Now with the rectangle, these are easily defined. All I need is a lower limit for x, an upper limit for x, and we're going to use the usual variables that we use to represent an interval on the x-axis. We're going to say x goes from a to b, and then I need something similar on the y-axis. I need a range for the y, and again, typically we use c and d when we're referring to limits on the y-axis. So our rectangular region is defined by, and what we can do is, so here are a couple ways that we're going to denote this rectangular region. So we could say that R is the set of all ordered pairs where X can be any number from A to B, so like this, and Y can be any number from C to D. So this is, you're going to see this sort of notation quite a bit when you're defining a rectangular region. And you can tell right away that it's a rectangle where all four limits, right? The pair of limits for x and the pair of limits for y, all four limits are constants, right? That defines a rectangular region. Another way that the rectangle could be defined is using a special set operation, which is called a Cartesian product. So this is not your cross product, but it's called a Cartesian product. So an alternative way to define a rectangle or to denote a rectangle is this. And basically what it is, you pair up every x value between A and B with every y value between C and D. So this is what it looks like. So you basically say you take the interval A to B, and notice we're using the square brackets because the endpoints are included. Notice I use the solid lines all the way around for this boundary or these boundaries. So you take the interval AB and you do what we call a Cartesian product, and we use the same x, and you essentially take the product of the other interval C, D. And the x interval is always given first, and then the y interval is always given second. So these are the two common ways to indicate the rectangular base for our solid, right? Next up, as far as our surface is concerned, we've seen this notation a lot, so we're going to use z equals f of xy. And again, it's going to, most of what the work that we're going to do for the double integrals, our z is going to be expressed explicitly as a function of x and y, right? And again, under the assumption of continuity, we're going to find out that it's really not that difficult at all to compute these volumes, right? So remember our notation was this. So in general, when you had a region, it didn't have to be a rectangular region, but we denoted the double integral like this, right? Where again, the dA represents the area of the base, the tiny area of the base, And then the fxy represents the height that's defined by your z value. And then we're just saying that, okay, yep, we're going to integrate over this region and get our solid, right? Well, let's kind of do it not completely in reverse, because we're not going to go back to the actual summation. But remember, dA, as I said, it represents the area, the very tiny area of a very tiny rectangle. Let's say that's my little rectangle there. And I could represent that as the differential dx, and I could represent that as the differential dy. So this very, very small, the infinitesimal length and the infinitesimal width. So in the rectangular coordinate system xy, this dA can be represented in two ways, right? So in a rectangular coordinate system like the one that we've started out with, right? In fact, it's the only coordinate system we've used up to this point. So in a rectangular coordinate system, and dA is equivalent to the differential of x times the differential of y, or it would also work the same, you'd get the same quantity if I took the differential of y times the differential of x. And again, just think of the d's as representing something very, very small, something infinitely small. An infinitely small width along the x-axis, an infinitely small length along the y, and when you multiply them, you'll get an infinitely small area, and that represents the area of one of those really tiny, tiny rectangles. And then when I multiply that by the height, I get that little sliver of volume. And when I do it over the entire region, I add all those volumes together, right? So the dA, we can break it up as dx times dy or dy dx. And then that actually gives us two possible ways of integrating this, right? So that takes care of this part, but then what do we do with these two integral signs? Well, I know that the range of values for x, I know the range of values for y. So maybe I can represent the intervals a, b, and c, d also using this notation, right? So what I'm going to write down now is something that, or two things that are referred to as iterated integrals. Iterated, right? So an iterated double integral. So our iterated double integral. And let me underline that. Let's do all of these. Is of the form, right? And so let's say we were to do the dx dy option, right? So let's say we represented dA like this. So I'll kind of write it in reverse. I have dx dy, then of course I'll still have my surface, my function. It looks like this. And then with these two integrals, so now instead of just putting the generic r, I can say, well, this region can be represented like this, where the limits for x are a and b. So what I'm going to do is put the a and b there, and think of this as, so I'm going to put square brackets, so like this, right? Right? And then let's say after I figure out a way how to compute this, if I then take the limits for y, the c and d, and put them right here, right? So then that these outer limits, right, c to d, correspond to my outer differential, and then the inner limits corresponds to the inner differential. So this is what this is one example of an iterated integral. And you're going to see in a second why we use the word iterated. But we're saying over here that our area, or tiny area, can be represented in multiple ways. So what if I were to do a similar thing but then choose to do dy dx? I would still have my surface there, right? But then now this inner integral, which is sometimes that's how it's referred to, that integral would correspond to my variable, my independent variable y. And y, we know, ranges from c to d. So now I would have to put the c and the d there. And then after, if I can figure out a way how to evaluate that, right, whatever that is, then I would integrate the result. And now with respect to x, with x going from a to b. And the interesting thing is, it turns out that whether we represent our dA as dx dy or dy dx, once we have a method of evaluation, they will produce the same volume, right? So we will actually have a choice as far as how do we go about evaluating this iterated double integral. And there's a theorem by an Italian mathematician named Fubini that says an iterated double integral over a rectangular region, these two are always guaranteed to be the same. So let's go ahead and write that theorem, and then finally figure out how to evaluate this. So here's our theorem, and this is Fubini's theorem. Right, and I'll say this, so let z equals f of xy be continuous. So let's assume that we have a nice continuous surface, right? So be continuous over, and I'll define my rectangular region using this new notation so we get used to it. So over the rectangular region AB crossed with CD. And again, just as a reminder, this is the interval for X. This is the interval for Y. So if we have a continuous surface over a rectangular region, Fubini says, hey, we have a choice as far as how we can evaluate this. So the double integral over this rectangular region can be evaluated two ways. So I'll write down the first way, and the way we say it is we're going to integrate with respect to x first, then with respect to y. So I'll write it like this. And just for now, I'll drop the square brackets, right? But yeah, so you have your surface, and you can choose to integrate with respect to x first, but x goes from a to b. And then after that, we integrate with respect to y, c to d, and we will get the exact same result if we were to change the order of integration, meaning I switch these two differentials and I switch my limits. So I could choose to do dy dx, and my surface stays the same, but now I will have the cd as my inner integral, and then the AB as the limits for my outer integral. And that's what good old Fubini says that we can do. All right, so let's see how this actually works and what we can do to actually compute this. All right, so let's take a look. So let's just do quite a few examples now. All right, so I'm just, what we're going to be doing is computing all these double integrals. So there's nothing more to the question. So each one, I'll just state the surface, and I'll state what the rectangular region is. And then maybe what I will do in certain instances is just sketch the region. I'm not going to sketch the surface because, as we've seen, some of these are, pretty difficult, and my artistic ability is sketchy at best. So let's not push my artistic ability to my limit. So let's say the surface is 6 6xy squared, right? And let's say our rectangular region is, and again, I'll use this notation, 2, 4 crossed, or really it's the Cartesian product with the interval 1, 2, right? And what we want to be able to do is write down or evaluate the double integral, right, of this surface over this region, right? And I think it's good to, sometimes you might say, well, do I overuse the notation and I write a lot? But it's good to do that. You kind of build that muscle memory. The more you use the notation, the more you get used to it, and then you'll know, the appropriate use of it, right? So let's say we were to set it up using this form where we're going to have our differential as dx dy, right? So then it would look like this. I would have 6xy squared, and then I'd have dx dy, and then what I'm going to have to do, essentially, I'm going to treat these as two separate integrals, right? The first one, we're going to integrate with respect to x, and the limits are 2 and 4. And then the second integral will be with respect to y, and those limits are 1 and 2. Now, again, the reason why we refer to it as iterated is because we're going to do one after the other. And how we evaluate it is by working from the inside out. So let me put those square brackets again. So we're going to start with that integral, come up with a method of evaluation, and we can still use our fundamental theorem, and you'll see why in a second. And then once we figure out what's in the red brackets, right, then we will take that expression and integrate it with respect to y. So let's actually do it literally, iteratively, by doing this integral first. So we'll do, it's not really a step, but I'll call it step 1. So we're going to figure out a way how to do this. The integral from 2 to 4, 6xy squared with respect to x. And this idea of with respect to x, we are going to take what we developed for partial derivatives and kind of flip it and reverse it. Because when you think about it, integration is supposed to be the inverse operation of differentiation. So whereas, we had a partial derivative, even though we technically don't use this phrase a lot, but you can think of this as a partial integral or a partial antiderivative. And with that idea, what we get to do when we are integrating with respect to x, we get to treat y as a constant. So the same way when we were doing a partial derivative with respect to x, we got to treat y as a constant. Same thing now. When we're integrating with respect to x, right, we get to treat our other independent variable as a constant. And what does that mean? Well, this is a constant multiple. And when you're integrating, if you have a constant term, so I'm going to highlight this and say this is for this iterated integral, or technically we could call it a partial integral, we get to treat this as a constant. So this is treated as a constant. What do we do with constants constant multiples, I should say, when we're integrating? Well, we get to factor them out. So I can literally factor out the y squared and do this. Put the y squared outside, and then what do I have? What do I multiply? I'm multiplying the definite integral from 2 to 4 of 6x dx. So now when I look at this looks like a regular integral, right? And we treat it as such. And that's why we get to use our fundamental theorem of calculus. So I'll continue to bring down the y squared. Now let's write down the antiderivative of 6x with respect to x. So that is 3x squared. And we use the same notation. Now, you could do this if you wanted to. Now that you have, again, multiple variables in your integral, you could literally, if you wanted to sort of bracket this off and say that we're using the limits x going from 2 to x equals 4. So you could do that. You can see in some problems it is nice to kind of have the reminder here that what we're substituting for now is for x. The y doesn't change. It's treated as a constant, so we just bring it down in this instant, and then we're going to plug in x equals 4 as our upper limit, x equals 2 as our lower limit, and then use our FTC. So this is what we're about to do. So I'll put it above the equal sign. We're going to use our good old trusted fundamental theorem of calculus on this. Find the antiderivative, evaluate it, and then take a difference. The only thing is we just keep bringing down this other y squared. So then it looks like, so we have 3 times 16 minus 3 times 4. So that gives us, let's see, what do we have here? So y squared, so this is 48 minus 12, so we got times 36. So after doing the first of our two iterated integrals, we get a value of 36y squared, right? So what we have in the square brackets, the red brackets here, that is equal to 36y squared. And then we take this result and integrate it with respect to y from 1 to 2. So we could do it, we could do like a step 2 down here. And I guess since we have a step 1, we might as well go ahead and write this down as a step 2. Take this result, right? And now integrate it with respect to y, right? So we set it up like this. And then what we have is another regular integral, right? Again, it's one after the other, right? It's literally double the pleasure, double the fun. So let's go ahead and find the antiderivative now with respect to y. So again, using our power rule for antiderivatives, we're going to end up having 12y cubed. And then we're going to evaluate that at 1 and at 2, again, using our FTC. So I'm not going to write the FTC all the time, right? Because it's going to be as natural as it has been up to this point. It's just we get to apply it twice. So then we have our 12 times 2 cubed, that's 8, minus 1 cubed, that's 1. So that's 12 times 7. Drum roll, please. And we end up with 84, right? And then again, interpreting this as a net volume, we could say that this is 84 cubic units, right? Now, if we happen to know if the surface is like always positive over this rectangular region, then of course we don't have to refer to it as a net volume. But just to be safe, because it's hard to tell just by looking at some of these surfaces whether things are positive or negative, we can go ahead and refer to this as a net volume, right? So that's the process. Now, we could have done this problem the other way by doing dy and then dx, but since we've already evaluated this, let's look at another problem, but do that one with the order switched. So instead of integrating first with respect to x and then with respect to y, we're going to switch it and apply Fubini's theorem that says over a rectangular region, and that's key here, over a rectangular region, the order in which we perform our iterated integration does not matter. It doesn't change the result, right? If you wanted to, in fact, that would be a good exercise for you to do this problem again, change the order of integration and see if you get the 84, right? Go ahead and explore. Be my mathematical explorers. But let's charge on with another challenge. So let's look at a second one. And again, usually the first few double integrals that we do, we don't really look at the super complicated surfaces. Not that they're going to get overly complicated, but I tend to work with like polynomials since they're easy to work with. So let's say this is our double integral. Here's our surface. And let's say our region. So now I'll show you what it would look like using the set builder notation. So our region is a set of all ordered pairs such that, let's say x is between -5 and 4. And let's say y is between 0 and 3, right? And just to kind of sketch what the base is, not hard to see what the base is, but let's say we sketch just the xy plane. So y goes from -5 to 4. So let's say -5, let's say that's 4. And x, goes from -5 to 4. Forgot an inequality there. And then y goes from 0 to 3. So this 0 would be our x-axis. And let's say this is 3. So then, yeah, just sketch the rectangle that has those bounds. And this is the base of the solid, right? So this would be the base, or this is the region over which it's being integrated. And I'm looking at this surface with that minus sign there. I'm going to go out on a limb and say that this surface, part of it is above the xy plane and part of it is below, right? So it's like the solid is going to be between this surface and this rectangular region in the xy plane. In fact, when we did that video with the visualizations, we saw one where, yeah, the surface literally cut through the xy plane. I'm gonna just kind of fathom a guess that this one does that thing. All right. But regardless of what it looks like, we now have a method of integrating. So let's do this one where we do the integral with respect to y first and then with respect to x. Right? So when we set it up as a double integral with the specific limits, I would have to put my y limits first. Right? So y goes from 0 to 3. And then x goes from -5 to 4. And then here's my surface, the 2x minus 4y cubed. And then in terms of the order, it will be dy dx. Now in the previous example, we literally broke it into 2 steps where I did this one separate and then I did this one separate. I want to show you that it is possible if you like to keep all your work together instead of breaking it up literally as these 2 iterated integrals. You can still do the iterative process, but you can keep everything together. So this is how it would look, right? So we are going to do this first. Now, when we're integrating with respect to y, we're going to treat x as a constant, which means any term or factor that has an x is going to be treated as a constant, right? So let's just make this note. So we're going to treat x as a constant and integrate with respect to y. Now, this constant term is different from the previous constant term because this is not a constant multiple. This is a constant separate, and then something else is being subtracted. So think about how, for instance, if I had to, let me just show you this. Let's say we had to integrate 3 minus 4y cubed with respect to y. Well, if you were just doing this and whatever the limits are, so since this is a constant, then the integral of 3 with respect to y would give me 3y. And then over here, I would have minus y to the 4th, and then there would be a plus c or something there, right? So the thing is, if you have a constant term and you're integrating with respect to y, the antiderivative is whatever that constant is times y. So I get to use that principle here. And again, this is going to, let me keep this in green. This is going to be my constant term. So when I do the integral with respect to y, all right, so again, remember, I'm keeping everything together, right? If you like to do your work like this, it would look like this. So now let's write down what the antiderivative of the surface is with respect to y. So it is going to be 2x, that's my constant, times y, and then minus, then yeah, integrating this with respect to y, add 1, divide by the power. This is going to give me y to the 4th. And then this is where that kind of square bracket notation is helpful. And then these are y limits. So we're going to plug in y equals 0 and then y equals 3. And whatever this whole thing comes out to be, then we're going to integrate that result with respect to x. So this is what it looks like. You can keep everything together, but again, it's still an iterative process, one integral at a time, right? So let's bring this down. So from -5 to 4. Now let's use our fundamental theorem and evaluate. So at the upper limit, let's see, we're going to have 2x times 3. So that's 6x. And then I'm going to have minus 3 to the 4th power. That is 81. And then that is the function now that I'm going to integrate with respect to x, right? And let's see what we have. So this is going to give us 3x squared minus 81x. And again, another FTC. We're going to plug in our 4, plug in our -5, and take a difference. So, oh wait, I forgot an x here. This is minus 81x. Here we go. So we're going to have 3 times 16 minus 81 times 4. That's times. And then minus 3 times 25. And then minus 81 times -5. All right. And just looking at this, yeah, because this is going to be a big positive number, but then you're subtracting it, and we're going to end up getting -756. And if we think of this as volume, there's that negative sign. And what this tells me is that more of the solid is below the XY plane than it is above. So in other words, that's why this number comes out to be more negative than positive. And we can still refer to it as units or cubic units, or in terms of cubic units, but we now have to interpret it as a net volume. So more of the region or solid is below the XY plane than above. All right. So there we go. That's our process for evaluating double integrals, and we do it in this iterative fashion. But it works well because our region is rectangular. In our next set of videos, we're going to see, well, what if our region is not rectangular? What do we do then? Well, if you want to find out, hop on over to the next video. See you then.